In this example problem, we're going to use energy conservation to figure out how high a projectile will go when it's been launched from the surface of a planet. Let's say the projectile, this little red dot, has mass little m. It's got initial launching speed v sub 0. The planet it is launched from has mass capital M and radius capital R. And we want to figure out how high above the surface this projectile goes. Let's assume that this planet has no atmosphere, so it'll have no air resistance. Okay, now we could imagine trying to solve this problem different ways. One way we might try to imagine solving the problem is to find the force that the planet of mass m exerts on this projectile. Try and calculate then the projectile's acceleration, and using the acceleration try and figure out the maximum height. Well, that's not going to work out very well for us because as this little mass m gets further and further from big M, the gravitational force will get less and less and less in magnitude, and therefore the acceleration will get less and less and less in magnitude. So we'd have to do a series of integrations. First integrate the acceleration to get the velocity, integrate that, which is ever changing, to get the change in position, and it's going to be a big hairy mess. So our easiest route is going to be to use energy conservation. So let's see how that works out. To use energy conservation, we need to consider a system to apply energy conservation to. So our system is going to consist of the planet of mass capital M and the projectile of mass little m, and that's it. We basically have, for all intents and purposes, an isolated system, so the change in energy of this system is going to be zero. Within this system, the only forms of energy that are changing are the kinetic energy of this projectile of mass m and the gravitational potential energy of the system consisting of this mass m and the mass of the planet. That's it. So we plug in the appropriate expressions for these energy changes, and we can also note that at the maximum height, our final velocity, if we take that to be the instance of the maximum height above the planetary surface, that speed at that height will be 0, so v sub f is equal to 0. And in the remainder of the expression, we notice that we can cancel out the mass. Finally, we can multiply through by 2 and rearrange to get the following expression. Now, first note, this is not yet the answer. What we found is the R final, where R, that's the position of the projectile relative to the center of the planet. That's measured from the center of the planet. So we found from here to here. That's R final. What we want is this distance h. How high above the surface does the projectile go? So we need to subtract one planetary radius, capital R, from R final to get h. Now we should of course do some reality checking with our answer. I will leave checking the units to you. The units do work out. But what I'm going to do here, my reality check, is going to be to consider the case, what if the initial launch speed v sub 0 was 0? If v sub 0 is 0, then that's gone. Boom. Then in this term we'd have 2gm over 2gm over r. So the 2gm's would cancel, and the 1 over r would just become an r. And h would be r minus r, which would be 0. And that makes a lot of sense. If you don't launch the projectile with any speed, it's not going to go any distance above the surface. The h would be 0. So that checks out. Finally, I want to discuss the conditions or limitations on this answer. So consider this. What if v sub 0 squared was bigger than this term? Then I'd have a negative, then this minus v sub 0 squared would give me a negative number, which give me a negative number here, and I have a negative number minus a positive number gives me an even greater negative number. So I'd have a negative height. What could a negative height possibly mean? Well, whatever it means, it certainly isn't physical. And here's the reason why. There's a certain speed, and it turns out to be, for speed such that v sub 0 squared is greater than this value, that there is no maximum height. the projectile will just keep going on and on and on and on forever. In other words, when v sub 0 squared is greater than this value here, the projectile will entirely escape the planet's gravitational field. For that reason, we call that value of v sub 0 the so-called escape speed. But really, we should call it the launch speed necessary for escape.